All right. Raise your hand if you have ever been in a position at any point in your life where you've ever had to sort anything. Put up your hand. Obviously you have. Obviously. All right? And in order to do that, if you ever had something you needed to sort, you needed to, assuming you didn't start with an already sorted collection of things, you needed to sort it by following some set of rules that, let me ask you this. You needed to sort something. Were you successful in your endeavor of sorting things when you needed to? I thought so, right? So you needed to sort something, you were capable of sorting things. Congratulations, you did it. But how did you do it? You all did it, obviously. So how did you do it? What did you do to actually get that collection sorted? You would have followed an algorithm. What was it? So take a moment, close your eyes, think about the last time you sorted anything. Imagine you've got a stack of pages with just big numbers on it, and they're not sorted. And I say, okay, go sort it. How do you do it? Take a moment, seriously, take a moment, give yourself 30 seconds to actually think about it. I'm not being silly. Sorting is a heck of a problem. So think about it. You can talk amongst yourselves if it helps you work through it. So hopefully by this stage, you've got an idea. Now before, I'm gonna cut it off before it happens. Every year there's some person in the room that tries to impress me with their trivia on sorting algorithms. And they'll say, oh, this is how I sort things, which there's no way it's true because the amount of space it requires is just impossible. But they'll start explaining a really sophisticated sorting algorithm as if it's going to impress me. Don't do that. You're not going to impress me that you know a first-year sorting algorithm, okay? What I'm more interested in is that you were able to think about an actual sorting algorithm that you actually would do. And I'm willing to bet what all of your ideas that you've just had, I'm willing to bet they are going to be one of, if not some combination, of the three algorithms that we'll talk about for this topic. There are insertion sort, selection sort, which are basically the same thing, and then bubble sort. My guess is you've followed these algorithms when sorting things before. Now there's a bit of a disclaimer here at the top. These algorithms are far from trivial. The problem of sorting things, yeah, it's trivial. My 1-year-old was able to do it, they sort blocks, right? Based on, yeah, okay, sorting as a problem is easy to understand, and that's why we like it as programmers. It's not that sorting is some critically important thing. Don't get me wrong, it is. Sorting obviously is an important thing. But the reason that we talk about sorting is because it's an easy to understand problem that actually has some interesting nuance to it. And it gives us a chance to really think about our algorithms and what's good about them, what's bad about them, what makes this one better than this one, and vice versa. So it's a really good environment for learning stuff. But these are non-trivial algorithms. And sure, some of the earlier algorithms we've talked about, we could say are non-trivial, but like think back to like converting Celsius to Fahrenheit. The only reason that was not trivial, non-trivial to you at the time was because you were learning like the syntax, right? If I asked you now, go write an algorithm to convert Celsius to Fahrenheit, you should be able to do it like that. Sure, you might have to look up the formula, but like you could do it. That's a trivial algorithm. Searching, that's a non-trivial algorithm, right? But don't get me wrong, the sorting is less non-trivial. Less, it's harder. So sorting it's a tricky problem. So just like don't conflate the problem, we need to sort things, with the algorithm, the steps that we will follow to achieve the problem. Don't conflate these things. Obviously they go together, but there's a separation there. In order to when I present these algorithms to you, I'm going to do it in a way that makes it hopefully as easy for you to understand as possible. But it is not reasonable. It's entirely possible for me to give you the intuition behind each of these algorithms and be like, yeah, I get it, right? But I'm not going to stand here expect you to have a full and complete understanding of these algorithms from just showing them to you. These would take time to think about and go through on your own in order to really wrap your head around them, okay? So don't get spooked by them. Don't think that it's futile to listen to me right now. That's not the point I'm making. Listen to me. But you're not going to have a full comprehension of them beyond intuition after a lecture on them, okay? Yeah, okay, cool. And a note, too. Each of the algorithms I'm about to show you have a lot of different implementations. I'm just showing you one of many implementations. It's not even necessarily a particularly good implementation of each of these algorithms. But I'm going to show you an implementation. And remember, too, how also before, there's been messaging I've been giving you about how many ways are there to solve a problem? Well, literally infinite, right? But a lot of what we've talked about is different ways of implementing the same algorithm to solve a problem. Okay, great. But there are different algorithms, entirely different algorithms, not in terms of how they're coded, but in terms of their whole structure, in terms of the steps and order that you do things. The algorithms are entirely different, but they can still solve the same problem. So, okay, I told you, imagine you had a big stack of papers in front of you with, and they're unsorted, okay? How do you sort those things? Who can give me an idea of what are the steps they followed to do that? What are the steps that you would do? Actually, if I gave you a pile of paper right now, I wish I had a pile of paper. I thought about making one after talking to you at office hours. I should have done it. What are the steps you would follow? Who can give me some ideas? So go through and find the smallest possible thing. Yeah, and then what? So I go okay, I found it, perfect. Now what?
Place it on top and look for...
Put it on top, okay, great, yeah.
And then look for the one that's the second lowest?
Second lowest, or if duplicates are allowed, I guess you could equal or, yeah. Okay, yeah, okay, cool, and then you just keep going.
Yeah.
Okay, that's actually called selection sort, which is the first one that we're doing. Literally what you just described. You didn't cheat, did you? Cheat by looking like a sliver below. So what is it doing? It goes through. So you said find the smallest thing. Well, how would you do that? Well, you would do a linear search, right? You would go through and you would find the smallest thing. How do you do that? You do a scan and say, okay, is this the smallest thing? Let's watch, right? Okay, 8, 2, we found 0, perfect. You see? It's doing a scan to find the smallest element, and then it puts the smallest element on the top. We could have put it on the bottom. We could have, whatever, just implementation issues. But we go and we put it on top. Then we do it again. 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 And it appears that this would sort the collection pretty well. Do you agree that this is what you described to me?
Yeah.
Yeah. How about that? So here's a, perhaps, this is like an in-place one. We can think of a different one. Imagine, well, we won't do this right now, but imagine I wanted to sort everyone in here based on height. Okay? And I would put everyone over here. The order that they exist in over here doesn't really matter. They could just be in a giant blob over here. It doesn't matter. You're just standing in some group. Okay? And this is the unsorted group. And what I'm going to do is I'm going to go through the unsorted group and find the shortest person. Okay, you come with me. Stand right here. This will be my sorted collection. Would you agree that this is now sorted? I mean, there's not all of them, only like there's one person in that list. But would you agree that a list with one thing in it is sorted? Is it unsorted? It's kind of a funny little fun thing, right? Anyways, I'll do that again. Of those that are remaining, who's the shortest? Take them out, put them here. Do it again. Here. So as I go, the list of, or the collection of unsorted things is getting smaller and smaller and smaller. And every time I find the smallest thing, I just append them to the end of the list of sorted people. Now, why does this work? So our intuition is like, well, obviously it's going to work. But think about it. Imagine we're at some arbitrary point in time of executing this algorithm. Let's say there's n people that need to be sorted. And there's about n over 2 left and about n over 2 in here. Okay? So like, am I like, how do I know this is going to work? Am I guaranteed that this is going to work? Well, think about it. Let's say I go in here and I find the smallest person in here, the shortest person here. Okay? How do I know they're the shortest person? I did a linear search for them. Okay? So I take them out, I walk them over here, and I'm going to append them to the end. Okay? How do I know that's where they go? Is it possible that they should have gone earlier in the list of sorted? Well, no, because if they should have come earlier, they would have come earlier. Because over here, when I was taking the shortest person, the one round before, let's say, okay, the round before, I said I'm at that n over 2 point, right? So let's say this is the round right before that. I go select the shortest person. The next time I come back, I select the next shortest person, right? I can't pick them out of order because I'm always picking the shortest person that's left. So the shortest person that's left must be taller, or at least not shorter, than the person that was removed before them. Obviously. So that's how I know, I can guarantee, yeah, this will work. We can rationalize this perfectly fine. That's selection sort. You go through and you select the next thing based on where it should go. Now this implementation here, you can kind of see how we're, with my mouse, it's like, well, there's only one collection here. Yeah, but like the yellow shaded area is like the sorted part. You see what I mean? Yeah. Any questions about that intuition at this stage? All right, so it's fairly accessible, and chances are you've used this in real life. Raise your hand if you're like, yeah, I've done this. Put your hand up. Of course you have. It's so obvious, right? Selection sort works by repeatedly selecting the smallest element from the collection. The high-level algorithms as follows. Start with an unsorted list and an empty list of sorted elements. For each element in the collection, perform a linear search on the unsorted list for the current smallest element. Remove it and append it to the end of the sorted list. There you go. The reason it works, consider the first time the linear search finds the smallest element, that element must be the first element in the sorted collection. Every subsequent linear search finds the remaining smallest element and it appends it to the sorted collection. It cannot come before anything in the sorted list, sorted collection, since we know it must be greater than or equal to all elements in the sorted collection. Otherwise, it would have been selected before. Right? Sometimes when you're talking about like these intuitive proofs, it's kind of hard to appreciate like the significance of the statements because it's like, duh, obviously. Why didn't I pick 7 before I picked 2? Because 7's bigger than 2. But why didn't you? Because it's bigger than 2. Based on the algorithm, I must have picked 2 before I picked 7 because I can't pick 7 before 2 because 2 is smaller than 7. So that's why sometimes these intuition ideas of how they work are hard to grasp because it almost sounds like too obvious. But it's important to make sure we can really rationalize these things to ourselves. So let's do this. We'll do this together, right? Let's perform this search right now, or sort. 374152. 3, 7, 4, 1, 5, 2. Okay? So, there's an eraser, right? So this is the unsorted U. This is the sorted. It starts empty, right? Hold on, again, here's my empty list. Okay, an empty list. Is that sorted? Is an empty list sorted? It's not unsorted. It's kind of a funny little thing to think about, right? Would it be wrong? Now, this is what's really fun and annoying about computer science, is we get so worked up about how things are defined. And I know sometimes it can feel like, and it's kind of hard to, this is something you don't really get an appreciation for through experience. If I gave you we're hitting pause on selection sort. I'm going to go over here for a second. If I draw over here, will you be able to see it, do you think, over there? If I have a list, you know what? No, we're gonna come back to this probably on Friday. I don't want to spoil the fun for Friday. That's I'd really be robbing you of quite the experience. So anyways, okay, here we go. Let's get rid of these. It doesn't matter. All right, let's go through this and find the smallest element. All right, 3, no, 1, okay, 1. So let's take out the 1, put it here. Great. Still sorted, still unsorted. Okay, 3, 2, okay, 2, great. Okay, 3, still there. Okay, the 3. 4. Okay, 5, 7. There we go. Cool. Selection sort. That's it. You go through, select the next smallest thing. Now, you'll notice that the sortedness is kind of defined by what do we want, right? Like I said, the next smallest thing. Really, is smallest really what matters? What if you want to sort them in descending order? What if you want to sort them by color, right? What if you want to sort them by... So when I say the next smallest thing, I don't necessarily mean it's always going to be the next smallest thing. It's well, what would the next thing be? What ought it to be, right? If I say, go sort these things by color, how do you do that? Well, your next question is, how? How do you want, if I say, here's a bunch of students, sort them, you're going to say, by height, by name, by shoe size? Like, what do you want, right? So what defines the ordering is a separate thing. I'm just using integers, which come with an intrinsic ordering, right? 1 is smaller than 2, because it is. Yeah. All right, so now that we know a little bit more about the algorithm, let's analyze it. How much work does this take? So there's like 2 parts of this algorithm effectively. The first part of the algorithm is do a linear search. And then once you found the smallest thing, the next part is just put the number, take it out, put it there. Then what do? Another linear search. Okay, yeah. And then we take the, put it there. Then what do? Another linear search. Okay, so let's say I have a list of length n. Okay? And I say, do a linear search. How much work is that? Think of that like if there's n things in there, how many things do I have to put my finger on to find the smallest? N, right? If I double it, 2n. If I quadruple it, 4n, and so on, right? So the amount of work, it's like, it's linear, it's n, okay? And by the way, listen up, this is critically important stuff. This is what it's all about right now, okay? N. So if we have to do a linear search on n elements, the amount of time doing one linear search, so one linear search is, we would say like order n. That means like on the order of n. That's a fancy way for computer scientists to be lazy, to be like, yeah, it's like n. Okay? But after I do one linear search, I take the number out, and then what do? Another linear search. How much work is that linear search? N minus 1. Yeah, you're right, it's n minus 1, but that's still like, yeah, it's like n. Right? I mean, really, okay, it's like n minus 1. Fine. I shouldn't put the O's here, because now we're doing something a little different. Next time, how much work is the linear search? How many linear searches do I have to do? N. Why? Well, there's n things in the list. You could say, well, you don't really need to do that last one, because when there's 2 elements and you take one out, you don't really need to search that last list because it's only 1 element, right? Do you see my point? Yeah? But at the end of the day, I have to do n linear searches, more or less. And if I have to do linear search n times, how much work is that in total? If I have to do n units of work, n times, how much is it? Yeah, that's n squared. It's quadratic. And by the way, for those of you, I was always puzzled until maybe this was me, and I just got too old and I missed this along the way. But if you're like me, around your age, when I was like, why do we call this quadratic? It's a 2. It's because it makes it a square, right? Quad, you know. That's why. Anyways, it's quadratic. Meaning that if you doubled the size of the list, it takes 4 times as long to run. Where with the linear search, if you double the size, it's 2 times. Now hold on. You might be thinking to yourself, hold on. I mean, you said n units of work n times, but it's not really n units of work n times. It's n units of work, n minus 1 units of work, n minus 2 units of work, and so on and so on and so on, right? So it's not really the same. And you know what? You're right. You're absolutely right. So let's take a moment and think about it, okay? So if I have to do n units of work plus n minus 1 units of work plus n minus 2 units of work plus 2 plus 1 units of work, right? Why did I do, well, okay, look, 1, 2, okay, yeah? Does this look like anything to you? Who here's passed grade 11 math? Maybe it's 12? Yeah, I thought, okay. Does this look like anything to you? What does this look like? Can anyone tell me what we call this thing? Maybe let me help you out here a little bit. Let me help you out a little bit. Not factorial, no. But I know why you're thinking that. I'm gonna rewrite it a little differently. 1 plus 2 plus n minus 1 plus n minus, oh no, let's just do n. What does that look like? Progression. A progression? Yeah, it's like a series of some sort, right? A series of a bunch of little like plus signs. What's another word for that? A sequence. It's an arithmetic series. Come on. Pardon? Yeah. It's an arithmetic series. And who remembers their story of, who is it? Euler or Gauss? I can't remember who's the story about. I don't know how true it is. It's probably an apocryphal story. Oh, come on. I learned this. I know that this was grade 11 math. I remember. What are they teaching kids these days? My goodness. Come on. What's this here? What is it? Is it Euler? I think it's Euler. I could be Gauss. I could be wrong. But the story is like a very famous mathematician. Was like being a little shit in math class when he was a kid. All right? And so the teacher gave him busy work, saying like, okay, well, go add up all the numbers from 1 to 100. Okay? That'll keep him busy, right? It'll keep anyone busy. And he comes back 2 seconds later and he's like, here. And the teacher's like, what? How the hell did you do that? He's like, well, obviously, look. It's a little function. We can pump thumb. We're done. Have you never heard this story before? All right. That's sad to me because this story, you know what? It was when I heard this story in like grade 11 where I had this realization where, you know, math wasn't handed down by the gods on stone tablets, okay? People somewhere were like, you know what? What if we do this? Hey, if we do this and what? Basically, a lot of the mathematics that we do, someone had to figure out, and they just kind of followed like some like operations and steps to make it do what they needed to do. Okay, look, okay. So if you want to know, if you're ever put in a situation where you want to know the sum of a series, assuming there's like a regularness to it, okay? There is a nice way to do it. You don't actually need to go and you don't actually need to go and do all like the math. You don't need to go and add everything up. You actually just do, what is it? N times n plus 1 divided by 2. I think that's it. Does that look familiar to anybody? Yeah? A couple people? You remember grade? Is it coming back now? Yeah. But why? And I hate to say this. I have a bad feeling that when your teachers taught this to you, they taught it to you as if this was handed down by the gods. This is the magic expression you use to find the answer. But there's a reason. Someone came up with this, and it makes perfect sense. And it sounds like he's describing it over there, which is great. That means at least one person in here knows. Here's how. So the problem here is like, okay, there's a couple of ways we can do this. What if we were to like, let's pretend there's like an even number, okay? Let's pretend there's an even number of elements in this series for simplicity. What is the sum of this and this? N plus 1, right? So we have an n plus 1. Now, what's the sum of this and this? What's 2 plus n minus 1? And then assuming there's a 3 plus n minus 2, what is it? Right? I think you're seeing a pattern. It's just a bunch of n plus 1s, but how many n plus 1s are there? However many n is, but it's actually, I took 2 elements to create one term. So it's not n, it's n over 2. So basically, it's, oh, I have n over 2 n plus 1s. Now, there's more to it if you want to be like, well, what's its gap and everything. We don't need to worry about it. But that's the idea. Is like, look, there is like a perfectly like algorithmic process that helped us arrive at this. Okay? Now, I think the way you were describing it was slightly different, but it still works. And I'll do it the other way. Is instead of doing it like that, is you could also, like, it's also common to see people go like, well, what happens if we do like, let's write it again, but in reverse order. Right? But the trouble is we just doubled it. So we'll have to remember we doubled something. So we'll just have to undouble it later. And then you go, oh my gosh, it's n plus 1. And then, oh my gosh, n plus 1. And then n plus 1. And then n plus 1. And so on and so on and so on and so on and so on. And how many are there? Well, there's n. But we doubled it, so we have to divide it by 2. Right? So the same idea. Cool, eh? I think that's pretty cool. Yeah. Anyways, so why was this important? Well, I wanted to sum up the total amount of work. And I'm saying that the total amount of work is that. Now, as it turns out, here, this is actually 1/2 n squared plus n. That is the total amount of work that that algorithm will do. Okay? Now, computer scientists are nice and lazy. And we really only like to focus on how things scale. Remember how I was saying, like, when talking about a linear search, I'm going on about, like, look, yeah, that's the total amount of work being done, but really what we're focused on is how much more work is there when it's scaled up? Like, how does the scaling go? And with linear algorithms, it scales linearly. Now, it's interesting because I could say, imagine, ignore this for a second. Pause on this. Imagine I have a linear algorithm that is actually like the algorithm, like the total number of steps that the algorithm takes is 4 times n, right? Because all I really care about is how it scales, I don't really care about the 4. Because if I double n, I double the amount of work. The 4 doesn't matter. The 4 matters in terms of like the absolute total number of steps, but I'm focused on how does it scale. And that's why something like this, I'd be like, it scales linearly. That's the O, right? Here, I see the half, and I'm like, I see the half, and I'm like, you know, the half doesn't matter. The half isn't going to affect the scaling. Another funny thing, too, is this right here, the n squared, what grows way faster? N or n squared? N squared. If I plot it, one looks like this, one looks like this. So I also don't even care about that part of it, right? Like that's inconsequential compared to the n squared part. So even though we're like, well, it's not really n units of work, n times, because it's like n minus 1, n minus 2, and so on and so on and so on, the algorithm still scales quadratically. So this algorithm is quadratic. You double the size of n, you quadruple the amount of work. And remember with binary search, if you double the size of n, how much more work was it? 1 more unit of work. Remember with the binary search, because it was logarithmic, which is pretty cool. So that's analyzing that algorithm like algebraically, I guess. But we can also do it like visually, like geometry based. Like imagine we have like an n square and an n square. The first time, it runs that amount. But for the next step of that algorithm, we actually only need to do n minus 1. So this is like n minus 1, n minus 2, n minus 3. And then eventually we get down to like here, right? Right? And then we go, oh my gosh, it's a square. But it's only like half a square. But it still grows like a square, right? So if you like pictures, you can draw pictures too to demonstrate this type of stuff. Long story short, this algorithm, do we agree that it works? Will it sort? Yeah. Do we agree that there's perfect intuition behind it? We can convince ourselves that it works, and we analyze the crap out of it more than you've probably ever thought about sorting things ever before. And you get a sense that like, okay, yeah. Have you ever noticed that the bigger the pile of things you have to sort, that much more of a giant pain in the ass it is? It's not just like, oh, it's twice as big, okay, it's going to take me long. That's why, I just spit. That's why when you like get a big pile of things to sort, you're always like, ugh, man. Because, yeah, as n grows, the amount of work you have to do grows non-linearly. It grows not exponentially, quadratically. I know it's confused. Don't worry about it. It doesn't matter. If things that grow exponentially are the absolute worst you ever could imagine. And actually, we can come to that in a second for fun. But yeah, so that's why if you've ever felt like, man, like if someone said, look, there's 2 people in the room. I've got 2 piles of things to sort. This one has 10 things in it. This one has 15. Which one do you want to, like, obviously you want to sort the smaller one, but you're like, man, I'll be a nice. The one that's 15 takes you way bigger, way more work, right? Adding 1 more thing to sort makes it not 1 more unit of work, a lot more than 1. So that's the story here. Is sorting like this, it sucks. Now I will say, spoiler, all of the sorting algorithms we're going to talk about today are quadratic. Not today, we're not going to finish them. But all the sorting algorithms we'll talk about here are quadratic. Turns out there are better ones. And what's wild is these sorting algorithms, like cave people were using. Because, I mean, I can only assume. I don't have record of it, but I can guess that that's what they were doing. So for millennia, this is how we did it. And it wasn't until like in the last 100 years where some people came along and they're like, wait, we can do this better, way faster, which is kind of crazy to think about. And by the way, here's why, like, have I talked about the traveling salesman problem to you? Have I used it? Perfect. We'll talk about this right now. Here's why analyzing your algorithms is important. Because it gives you a sense of what is entirely possible with computers. So, the traveling salesman problem is like this. Given a set of cities, okay? It doesn't need to be cities, but for simplicity, imagine cities. Okay, so let's say you're in Antigonish, and you need to go to, you're a salesperson, and you want to go visit every city today, and you live in Antigonish. So you start in Antigonish and you want to end in Antigonish. It's a Hamiltonian cycle. Don't worry about it. So you need to go to like 10 cities, towns in the province, right? So maybe you got to hit like Sydney, New Glasgow, Port Hawkesbury, Halifax, you know, and so on and so on and so on, okay? So let's say there's a bunch of cities, right? And I say, okay, you're here. And you've got a little briefcase. Okay? You start and you want to end here. How should you visit these cities? Should you do this? Should you go from here to 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 here? Oh, we missed one. Let's we bopped that one along the way. There. Should we do that path? Well, it would work, but I mean, I got to pay for my own gas. I don't want to spend that much money on gas. So I want to visit all these cities such that the total distance I travel is minimized. Now, it turns out humans are pretty good at this. You can look at a map and be like, well, I should probably do something like this. Right? I know it's hard to see, but you know, you can kind of figure it out. Now, turns out there is a hilariously simple algorithm to find the best path. And you will understand it as soon as I explain it to you. It's hilarious simple. Generate every possible path, calculate each path's total distance, pick the path with the shortest distance. Does that sound like it would work? Seems entirely reasonable, right? Great. It is a very simple algorithm. Does anyone know what the problem with this algorithm is? There's nothing wrong with the algorithm. There's something wrong with the problem, I guess, for lack of a better term. How many different paths are there? How many different orderings of 10 cities are there? Well, let's try to calculate this real quick, right? Let's say I'm here, and let's say there's 10 cities, right? So I'm here. How many more cities can I visit right now? So let's say there's 10. So okay, fine. One's fixed. So okay. How many choices can I make? Think back to like grade 6, where you're given that problem of like, if you have 3 pairs of shirts and 2 pairs of pants, how many outfits do you have? You just multiply them, right? So how many options do I have right now? 9. Assuming there's 10 cities, I start here, so I have 9. For simplicity, let's start with 10. 10. How many options? If I go to 1, how many more options do I have? 9. Then how many? Who said factorial a moment ago? It was you. Say factorial. That looks like factorial. Yeah, it is. Great. Yeah. So the total number of paths you have is actually, it's factorial. So if you have 10 cities, it's actually 10 minus 1. It's n minus 1 factorial. But for simple math, let's just say 10 factorial. 10. I mean, that's a lot. 1, 2, 3, 1, 2, 60, 36, no, 3,628,800 paths. Okay, that's more than I thought, right? Who would have thought there was over 3.5 million paths of 10 cities? Like orderings, right? Now, 10 is really small, too. 10's not even a lot. Like, what happens if you've got like 100? Times 10 to the 157. That's a lot of zeros. 157 zeros. To put that into perspective, how many particles are there in the universe? About times 10 to the 80. You could take each path of 100 cities and go to each particle in the universe. Assign each particle a path, and you're going to run out of particles really fast. Let's say you have an amazing supercomputer, okay, that can calculate one path distance every nanosecond. What is that, times 10 to the negative 9? Yeah? Is that right? Yeah. So let's divide that by 1. Okay, 1, 0, 0, 0, 0, 0, 0, 0, 0. Okay, yeah. Okay, yeah. Oh, that makes no difference. Okay, great. Okay. So let's say we could do that. That's how many. So that's how many we can do a second. Okay. Okay. So if that's, and then, okay, let's say I could do that for 60 times, for 60 seconds in a minute, 60 minutes an hour, 24 hours, that's like the day. I mean, look, I would need to calculate how many seconds in an hour have there been since the beginning of time? Quadrillion. Is that anywhere near? Look, that many. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15. Let's call it 18. 18 times 10 to the 18. If you had every supercomputer we've ever built, and it could calculate a path, like, imagine it could calculate like a quadrillion paths a second. We haven't even like touched the tip of 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 the iceberg in the time that the universe has existed. That's why it's important to think about the scale of these problems. Because if you naively think, I'll just calculate every path and pick the smallest, obviously that'll work. But it'll take hilariously longer, hilariously more, orders of magnitude longer than the universe has existed to even make a dent in actually doing that. So that's why it's important to think about this stuff. All right, we're over time. I'll catch you later. See you Friday.